Welcome to a brilliant integral from the country of India. We have this integral from 0 to infinity sin x by sin x dx, and sin x can be expressed in terms of e by e to the power x minus e to the power minus x by 2. Now probably you might be familiar that when there's something like e to the power minus x, we try to change it to the form of a geometric series with the following manipulation. We can multiply numerator and denominator by e to the power minus x to get e to the power minus x by 1 minus e to the power minus 2x. Now when x is running from 0 to infinity, for these cases e to the power minus x is less than 1. So that's why we can have infinite geometric series over here with the first term e to the power minus x and ratio e to the power minus 2x. And now we have 2 times integral from 0 to infinity. Sum for n is going from 0 to infinity, e to the power minus x and e to the power minus 2x times n. For this sum in the world of n, sin x is just constant, so it can be taken inside the sum dx. Okay, so now we can extend sum in the integral. Since this sum converges absolutely for every values of x, it's running in the integral, so we can extend the sum in the integral. Sum going from n equals to 0 to infinity, integral from 0 to infinity, e to the power minus x times 2n plus 1 sin x dx. Now we try to integrate this, and this is actually a kind of standard integral. We have integral of e to the power ax sin bx dx. This integral is something like this: e to the power ax by a square plus b square a sin bx minus b cos bx. Yeah, this is the standard formula, and it can be derived using integration by parts. Now for our cases, we have e to the power minus ax, and this b is just 1. And now for this modification, we will have minus a over here. This will be just a square. We will have minus a over here. We will not have any b. We will not have any b. And we will not have any b. So this is the integral for our case. It's going from 0 to infinity. It's going from 0 to infinity. So at infinity, the e to the power minus ax dominates, and it's extremely smaller than any of the other cases. We don't need to see these cases since it's dominative, and that's 0 minus at 0. This is 1 a square plus b square. This is 0. This is minus 1. So it's just minus 1 by a square plus b square, and b is 1. Okay, so I didn't want to say that. Okay, b a square plus 1. So 1 by a square plus 1 is the answer for this integral. Now for our case, a is 2n plus 1. So that's 2 times sum of n equals to 0 to infinity, 1 by 2n plus 1 whole square plus 1 square. Now we try to break down into partial fractions so that we can use diagonal functions. And to break down into partial fractions, we can consider the use of complex numbers. We can basically make it a minus I square, and then we can have 1 by 2n plus 1 plus I, and then 2n plus 1 minus I. And after this we can take out 2 common, so that we will have 1 by 2 over here, and sum from n equals to 0 to infinity 1 by n plus 1 plus I by 2 n plus 1 minus I by 2. Now to break this down, we can basically introduce I in denominator, and we can have this sum n plus 1 plus I by 2 minus n plus 1 minus I by 2. We can introduce this. Since the net effect of these two sums is basically just I, and we have introduced I over here, so that cancels out. And this helps us to break down these expressions into two partial fractions. 1 by 2i summation from n equals to 0 to infinity 1 by n plus 1 minus I by 2, and then minus 1 by n plus 1 plus I by 2. Okay, so now since we have these partial fractions, now we'll construct the use of digamma function for the manipulation. Basically, we have a formula that summation from n equals to 0 to infinity 1 by n plus x minus 1 by n plus y equals to digamma of y minus digamma of x. So if you want to look at its derivation, it's something like this. So basically we know digamma of x is minus of Euler-Mastroianni constant plus sum from n equals to 1 to infinity 1 by n minus 1 by n plus x minus 1. So this is the definition of digamma function in infinite series representation. And in a similar way, digamma of y will be negative of Euler-Mastroianni constant plus summation from n equals to 1 to infinity 1 by n minus 1 by n plus y minus 1. Okay, and now if we consider digamma of y minus digamma of x, we will get something like this expression. We will have 1 by n plus x minus 1 minus 1 by n plus y minus 1. So now digamma of y minus digamma of x, this, if we change the limits from 0 to infinity, we can have n plus 1 over here, and then 1 and 1 cancel out, so we have n plus x minus 1 by n plus y. So this was the derivation of this idea. Now if we have this formula, this will be 1 by 2i digamma of digamma of y minus digamma of x. So digamma of 1 plus I by 2 minus digamma of 1 minus I by 2. Now we can see that this thing over here, the other thing over here, just 1 minus the first thing, 1 plus I by 2. So you can notice this thing. Yeah, since 2 and 2 minus 1 plus I, that's 1 minus I. Yeah. And now we have a reflection formula in digamma function, that digamma of 1 minus x minus digamma of x is just pi cot pi x. So we have this formula in digamma function of reflection. And so if we use that, we first have to change the sign and change the order as well. And then minus 1 by 2i Now we have the same now we will have the same order, and then we can use the formula that gives us pi times cot 1 plus I by 2. We will have pi cot pi times this thing x, that is 1 plus I by 2. Now this is pi by 2 plus something, so pi by 2 plus something is just minus 10. Yeah, so 1 by 2i pi times this gives us minus 10 of pi by 2 2i. Yeah, so this was pi by 2 plus pi by 2i, and cot of pi by 2 plus something is just minus 10i minus 10x. So this is it, and now this minus sign will cancel out. Now we have pi by 2i into tan of something, but if tan of ix is equal actually I tan h x, so that is I times tan h pi by 2, and now this I cancel out. Okay, so that leaves us with pi by 2 tan h pi by 2. So that's a really elegant answer, and the solution was really beautiful. The journey and the process we went over, and the formula that we used, and the ideas that we applied, yeah, all of them were pretty awesome, and I hope you really enjoyed the solution. And yeah, do try similar problems and enhance your problem solving skill. And do follow us for more of such integrals from awesome integrals. And yeah, I hope you enjoyed the video. Thanks for watching.